Hello friends, welcome back to my YouTube channel. Today I will be discussing a numerical based on the McCabe Thiele method. This will be numerical number 2. In my previous video, I have discussed the first numerical where I discussed how to find number of ideal stages in a typical tree column. So this will be 31st part of my discussion on distillation, and I'm continuing my discussion on the McCabe Thiele method. Today we will discuss a numerical. This will be second numerical. That's why I'm calling it as numerical number 2. And here this particular numerical, you will learn how to find the number of ideal stages, and then you'll learn many other things. So let us first understand, or let us first look at the numerical statement. So you have the feed to a fractionating column is a binary mixture of 40% benzene and 60% toluene, and it is admitted at a rate of 14320 kg per hour. An overhead product containing 98% benzene and a bottom product containing 98% toluene are to be obtained. A reflux ratio of 3.5:1 is to be used. The molar latent heat of vaporization of benzene is 8085.97 calories per gram mole, and that of toluene is 9090.91 calories per gram mole. Calculate the molar flow rate of overhead and bottom products in kilomole per hour. The boiling points of benzene and toluene at 1 atmosphere are 80.09 degrees Celsius and 110.6 degrees Celsius respectively. Also find the number of ideal stages. Some additional is also provided to us. The specific heats of benzene and toluene are 82.44 joule per gram mole per Kelvin and 116.1 joule per gram mole per Kelvin respectively. The feed temperature is 295 Kelvin. The VLE data is given to us. So equilibrium values of X and Y are given to us. X is mole fraction of the more volatile component in the liquid solution, and Y is the mole fraction of more volatile component in the vapor mixture. So you have these values of X and Y. So these values are given to us. Okay, so let us first start with listing what information is given to us. So given data, you have what information is given regarding the feed. Feed is a solution of benzene and toluene, two components, benzene and toluene. Then boiling points of these two components are given to us. Boiling point of benzene is 80.09 degrees Celsius. That is 80.09 plus 273.15, which is 353.24 Kelvin. Then boiling point of toluene is given. It is 110.6 degrees Celsius. That is 1106.273.15, which is nothing but 383.75 Kelvin. So by looking at the boiling points, we can easily conclude that benzene is the more volatile component because it has lower boiling point. And then we are going to denote benzene by A and toluene by B. Then latent heats of vaporization for the two components, it is given. They are given. So lambda A, it is 8085.97 calories per gram mole. Lambda B is 9090.91 calories per gram mole. Latent heat of vaporization of benzene and latent heat of vaporization of toluene. Then specific heats of the two components are given to us. For benzene, that is CPA, it is 82.44 joules per gram mole per Kelvin. Then for B, that is toluene, it is 110.6 joule per gram mole per Kelvin. Then mass flow rate for the feed is given to us. It is 14320 kg per hour. I'm going to denote that by M. So M is 14320 kg per hour. And this has to be converted to kilomole per hour. So you'll be learning how you can convert mass flow rate of a feed, which is solution of two components. How to convert the mass flow rate into molar flow rate, that is kilomole per hour. Then composition of the feed is given to us. It is given as weight percentages. So percent weight of A is 40 and percent weight of B is 60. And we have to convert them to mole fractions. Okay. So this is also what we will be learning in this discussion. Then temperature of the feed is given. It is 295 Kelvin. Or then for the overhead product is nothing but the distillate or the top product. So its composition is given. It is given as weight percentages. So percent weight of A is 98 and percent weight of B is 2. Again, we have to convert these percentages, weight percentages to mole fractions. Then for the bottom product, composition is given. It is given as weight percentages. And what is the composition? Percent weight of B is 98 and percent weight of A is 2. And we have to convert that to mole fractions. Then the reflux ratio is given to us. Reflux ratio is 3.5:1. That is value of R is 3.5. VLE data is given to us. Equilibrium X and Y values, they are given to us. And what are we supposed to find? First, we need to find the molar flow rate of the overhead product or the distillate. And then we need to find the molar flow rate of the bottom product. And we also need to find the number of ideal stages required for this particular separation. So let's solving this. First, we are going to convert percentage weight to mole fractions. The composition which is given as weight percentages, we are going to convert them to mole fractions. Let us start with the feed. So in feed, you have percent weight of A as 40 and percent weight of B as 60. That means if you had 100 kg of feed, then in that weight of A would be 40 kg and weight of B would be 60 kg. That means I can use this information to get mole fraction of A in the feed, which we denote by XF. You remember A is the more volatile component, which is benzene in this case. So how is this calculated, the mole fraction? So you have WA upon MA, that is weight of A divided by molecular weight of A. This is nothing but moles of A. Moles of A. Divided by WA upon MA, again this is moles of A. And WB upon MB, where MB is the molecular weight of B. This are moles of B. So that means this formula is moles of A divided by total moles. Divided by total moles. So this is nothing but mole fraction. Okay, so in this way, you can convert the composition which is given on weight percentage basis to mole fractions. So very simple concept you can learn over here. Moles of individual moles divided by total moles. Okay, let me first erase this. So that means XF, which is mole fraction of A in the feed, it is weight of A divided by its molecular weight divided by weight of A divided by its molecular weight plus weight of B divided by its molecular weight. Molecular weight of A, that is benzene, it is 78. Molecular weight of B, that is toluene, it is 92. So if you put all the known values, XF will be 40 upon 78 divided by 40 upon 78 plus 60 upon 92, which gives us XF as 0.44. Okay, so a feed solution which has 40 weight percent of A in it fraction of A, mole fraction of A would be 0.44. Similarly, you can do the conversion for distillate. In distillate, percent weight of A is 98 and percent weight of B is 2. So if there was 100 kg of distillate, in that weight of A would be 98 kg, weight of B would be 2 kg. And again, XD, that is mole fraction of A in the distillate, would be WA upon MA divided by WA upon MA plus WB upon MB. Again, MA is 78 as we understood, MB is 92. If you put the values, XD would be 98 upon 78 divided by 98 upon 78 plus 2 upon 92, which gives us XD as 0.98. Now we need to do similar conversion for bottom product. For bottom product, the composition is percent weight of A unit is 2 and percent weight of B unit is 98. So in 100 kg of bottom product, there will be 2 kg of A and 98 kg of B. So that gives us XW, which is mole fraction of A in the bottom product, as WA upon MA divided by W upon MA plus WB upon MB. And where now MA is 78, MB is 92. So if you put all the values, you will get XW as 2 upon 78 divided by 2 upon 78 plus 98 by 92, which gives XW as 0.02. So in this way, the composition which is given to us on weight percentage basis, we have converted it to mole fractions. Then the next task is to convert the mass flow rate into molar flow rate. So mass flow rate, I denoted it with M, kg per hour. Now I will be converting it to F, which is kilomole per hour. So for that, I need to know the average molecular weight of the feed. So in order to convert kgs to kilomoles, what you do, you are dividing kg with molecular weight. But in this case, feed is a solution. It is a mixture of two components. Therefore, you have to use average molecular weight of that mixture. Therefore, the first task in this case is to find out the average molecular weight of the feed. So I'll denote it as M average. So M average is molecular weight of A into its mole fraction plus molecular weight of B into its mole fraction. So the formula is M average is equal to MA into XF plus MB into 1 minus XF. Why 1 minus X? You need to understand. There are only two components. You have XF, that is mole fraction of A in the feed. If XF is mole fraction of A in the feed, what would be the mole fraction of B in the feed? It will be simply 1 minus XF. Because mole fraction of A, if I denote it by A, XA, and mole fraction of B, if I denote it by B, this is equal to 1. So, and as per our notation, we are denoting it as XF. That is mole fraction of A in the feed. Mole fraction of more volatile component in the feed. Okay, so naturally or obviously XB will be equal to 1 minus XF. Okay, so in this way you can find the average molecular weight. So average molecular weight is M molecular weight of A into its fraction plus molecular weight of B into its fraction. Now if you use the values, you'll be getting M average as 78 molecular weight of A into 0.44 mole fraction of A plus 92 molecular weight of B into its fraction, it will be 1 minus 0.44. That gives average molecular weight as 85.84. Now, we will, once average molecular weight is known to us, you can easily convert kg per hour to kilomole per hour. So, F will be mass flow rate divided by the average molecular weight. Mass flow rate of the feed which is given to us, it is 14320 kg per hour. Average molecular weight we just found out. Therefore, F will be 14320 divided by 85.84, which gives us F as 166.82 kilomole per hour. In this way, we have converted mass flow rate into kilomole per hour. And for doing this conversion, we need to use average molecular weight, because feed is not a pure single component. It is a mixture, or it is a solution of two components. That's why we need to use the average molecular weight. Okay. Now, after that, the next step would be to find out molar flow rate of distillate, that is D, which we denote by using D, and then molar flow rate of the bottom product, which we denote it by using W. So for that, we are going to use steady state total material balance. What will be steady state material balance for the entire operation? Feed will be equal to distillate plus bottom product. Steady state material balance written for a distillation column will be F is equal to D plus W, and I am calling this as if I use the given values, F is 166.82, we have found out just now. That will be equal to D plus W. Both are not known to us, and I am calling this as equation number 1. Now, along with steady state total material balance, I will be using steady state material balance for A, that is for the more volatile component. So it will be F into XF, that is equal to D into XD plus W into XW. That is total feed flow rate into fraction of A, total distillate flow rate into fraction of A in it, total bottom product flow into fraction of A in it. So feed is known 166.82, mole fraction in the feed is known 0.44, that is equal to D is not known, but mole fraction in it is known, so D into 0.98. Similarly, W is not known, but fraction is known. So you have this equation, 166.82 into 0.44, that is equal to D into 0.92 plus W into D into 0.98 plus W into 0.02. That gives us this equation. So if you simplify it, you'll be getting this equation, 0.98 into D plus 0.02 into W, that is equal to 73.4. And now I'm calling this as equation number 2. Okay, so with equations 1 and 2, I have two equations, I have two unknowns. I can easily solve those two equations simultaneously and get the unknown quantities. So for that, what I'll do, I'll use equation 1. So from equation 1, what can I do? I will write equation for W. So from equation 1, W is 166.82 minus D. And I'll be using this in equation 2. So wherever W is there in equation 2, I will use this in that place. So it will be 0.98 into D plus 0.02. And now in place of W, I'll be using 166.82 minus D. That is this one. That is equal to 73.4. Okay. So I'll simplify it. This is 0.98 into D plus 3.34. Simplification, 0.02 into 166.82 is 3.34. And 0.02 into D is minus 0.02 D. That is equal to 73.4. Further simplification, that is 0.98 into D minus 0.02 D. That is equal to 73.4 minus 3.34. So this 3.34 is taken on this side and you get this. Then 0.98 D minus 0.02 D is 0.96 D, and 73.4 minus 3.34 is 70.06. That gives us D as 70.06 divided by 0.96. That is D is equal to 72.93 kilomole per hour. So in this way, we get the value of D. Now, in order to get the value of W, we are going to use this. So since W is 166.82 minus D, now you call D. So W will be 166.82 minus 72.93. That gives us W as 93.89 kilomole per hour. Okay. So in this way, we get the values of D and W. What is D? Molar flow rate of the top product or the O-rate product or the distillate. And W, what is W? The molar flow rate of the bottom product. Okay. Now let us move. Next. Okay. Now Next, we will find the value of Q. For that, what is known to us? We know that feed is at a temperature of 295 Kelvin. That is, in degrees Celsius, it would be 21.85 degrees Celsius. So that is how you got that. 295.273.15. That gives us the temperature as 21.85 degrees Celsius. So it is well below the boiling points of the components, and therefore you can conclude that the feed is a cold liquid. And at this point of time, you can just tell Q is greater than 1. We don't know the exact value. So how to find the value? That is what you'll be learning. So for that, we will be using the definition for the parameter Q. How it is defined? It is defined as the heat required to convert 1 mole of feed from its initial condition to saturated vapor divided by the molar latent heat of vaporization of the feed. Okay, so it is ratio of two quantities if you read carefully. So the heat required to convert 1 mole of feed from its initial condition to saturated vapor divided by the molar latent heat of vaporization. Okay, so out of this two, the heat required to convert 1 mole of feed from its initial condition to saturated vapor, I'll denote it by Q. How can you calculate this? Mathematical equation for it is Q is equal to Cp of specific heat for the feed into boiling point of the feed minus initial temperature of the feed plus latent heat of vaporization of the feed. There are two terms involved in this case. This is term number 1. So what does term number 1 give? It gives the sensible heat that is needed to take the feed from its initial temperature Tf to its final temperature or to the boiling temperature TBLM. So sensible heat, so you'll need to supply the sensible heat in order to take the feed solution to its boiling point, and then you need to supply the latent heat. So it will be sensible heat, the first term, and second term is the latent heat. Okay, so what are the terms involved in this equation? Let me tell you. The first one is Cpf. In this case, Cpf is the specific heat of the feed. This is not known to us. We know specific heats of the pure components, and we are going to use them to get the specific heat for the feed solution. Then TBLF is the boiling point of the feed solution. Again, this is not known. What we know are the boiling points of pure components, and we are going to use them to get the boiling point for the feed solution. Then lambda F is the latent heat of vaporization for the feed. Again, what we know are latent heats for pure components, and we are going to use them to get latent heat for the feed solution. Okay. Now, if we use this equation, definition for parameter Q would be simply Q upon lambda F. That is heat required to convert 1 mole of feed from its initial conditions to saturated vapor divided by molar latent heat of vaporization. That is Q is Cpf into TBLF. Okay, just 1 minute. This will be TBLF minus Tf plus lambda F divided by lambda F. So Cpf, TBLF, boiling point of the feed, and lambda F, they are to be found out first, as I said earlier. Okay, so let us do that. So Cpf, the specific heat for the feed, would be given by this formula. Specific heat for A into its fraction, specific heat of B into its fraction. Why fraction of B is 1 minus xf, I have already explained earlier. Okay, so now pure values are known to us. Pure specific heats, the specific heats for pure components are known to us. CPA is 82.844 joule per gram mole per Kelvin. CPB is 110.6 joule per gram mole per Kelvin. XF is 0.44. So if you use these values, CPF would be 82.44 into 0.44 plus 110.6 into 1 minus 0.44. That gives us CPF as 98.2 joule per gram mole per Kelvin. Then the boiling point of the feed. TBLF will be given as boiling point of A into its mole fraction plus boiling point of B into its mole fraction. So TA is given 353.24 Kelvin. TB is given 383.75 and XF is 0.44. So if you use these values, TBLF will be 353.24 into 0.44 plus 383.75 into 1 minus 0.44. That is TBLF is 370.33 Kelvin. The boiling point for the feed solution would be 370.33 Kelvin. So you need to heat the feed solution to this temperature in order to convert the feed into saturated vapor. Okay? So it is not, you can say this is the average boiling point of the feed. Average boiling point of the feed. Then lambda F will be calculated in a similar way. Lambda F is lambda A into XF plus lambda B into 1 minus XF. Lambda for A into its fraction, lambda of B into its fraction. So lambda A is given, it is 8085.97 calories per gram mole. Lambda B is given, it is 9090.91 calories per gram mole. XF is 0.44. So if you use these values, lambda F will be 8085.97 into 0.44 plus 9090.91 into 1 minus 0.44. That gives us lambda F as 8648.74 calories per gram mole. So Q, we had this equation CPF into TBLF. You please read it as TBLF. CPF into TBLF minus TF plus lambda F divided by lambda F. CPF we got 98.21 joule per gram mole per Kelvin. TBLF is 370.33 Kelvin. And TF, the feed temperature is 295 Kelvin. Lambda F we got, it is 8648.74 calories per gram mole. Now, since you have, lambda F is in calories and CPF is in joule, so we need to do the conversion. So you can either convert CPF into calories or lambda F into joule. And we are converting CPF into calories. And what we know that the conversion, 1 joule or 1 calorie is equal to 4.18 joule. Okay, so that is 1 joule is 1 by 4.18 calories. And we have got CPF as 98.21 joules. So 98.21 joules will be simply 98.21 divided by 4.18. So that gives us CPF as 23.4 calories per gram mole per Kelvin. Okay, so you can either convert joules into calories or calories into joule. Okay. Now everything is known to us. You can use the formula for Q. So the formula is Q is equal to CPF is 23.5 into TBLF is 370.33 minus TF is 295 plus lambda F is 8648.74 divided by 8648.74. That gives us Q as 1.2 and you must have noticed that what value we have got, it is greater than 1. So since we know that for feed as a cold liquid, value of Q will be greater than 1, and over here also we have got it to be greater than 1. Okay, so in this way we need to find the value of Q. Once you have got the value of Q, the next will be to plot the given data. Here, as was the case with numerical 1, where we learn how to generate the XY data by using the value of relative volatility. Here, the XY data is directly given to us. What is left? We just have to plot it. So, plotting of the VLE data. So, this is the VLE data that is given to us. So, by plotting it, we are going to get the distribution diagram. So, for that, X will be plotted on the X-axis. That is mole fraction of A in the more volatile, mole fraction of A in the liquid phase will be plotted on the X-axis, and mole fraction of A in the vapor phase, that is Y, it will be plotted on the Y. So if we do that, you are plotting X, small x on X-axis, Y on Y-axis. Then for reference, the diagonal line is drawn, and when you actually plot the data, you'll be getting points like this, and then I'll be drawing the curve through this, so that will give me the equilibrium curve. Okay, so in this way, you get the distribution diagram. Okay, the first step is we need to plot the rectifying section line. For that, we are going to use this information. XD is known to us, it is 0.98. And we also know the intercept made by a rectifying section line on the y-axis. It is XD upon R plus 1. XD is known, R is known. So intercept will be 0.98 divided by 3.5 plus 1. XD is 0.98 and R is 3.1. And so that gives us intercept as 0.22. Okay, so these two parameters, one is XD and the other one is intercept. We will use these two to plot the rectifying section line. So first we'll locate 0.98. 0.98 will be located at this point. So if you look at the scale, on x-axis 1 centimeter is 0.1. That means 1 division is equal to 0.02. And we have the same scale on the y-axis. 1 centimeter is equal to 0.1. That is 1 small division is equal to 0.02. So that's why 0.98 will be located over here. Yes, then I'll go to the diagonal line. And after that, I will locate the intercept. 0.22 will be located over here. I have this point, and then I can draw the rectifying section line through these 2 points. So the rectifying section line will be drawn in this way. Then next, we have to plot the Q line or the feed line. So feed is cold liquid, and we have got the value of Q. It is 1.2, and slope of the Q line is Q upon Q minus 1. That is 1.2 divided by 1.2 minus 1, which gives us slope as 6. Okay, so Q line starts at this point where x coordinate is xm. So let us first locate xm, 0.44. So 0.44 will be located over here. So from this point, I will go to the diagonal line. And now Q line is going to start at this point. This time, Q line is having positive slope. So if you have watched my earlier video, I have told how to plot line of the given slope on the XY curve. So here you have positive slope. Let me tell you once again, we are going to use the definition of tan theta. So why tan theta? Because slope of a line is nothing but tan of the angle made by the line with the horizontal. Okay, so in this case, tan theta will be, let this side be n, then m let this be N, let this be M. Let me pause. Sorry. So this is M, this is N, and this is S. So as per definition of tan theta is M upon S. And if S is made equal to 1, if S is 1, then tan theta will be simply equal to N. Are you understanding it? So this distance, we are making it to be 1. And then in that case, slope will be simply equal to the distance of the opposite distance. That is M in this case. Okay, so let us do that. Now here, slope, in this case, what will be the formula? Slope will be, I'm writing it like this. Slope is 6 upon 1. That means on the right side, I will be covering a distance equal to 1 unit on this graph. And then I will be covering a vertical distance is equal to 6 unit on this graph. So I can make this change. What change? I will divide by 2. Divide the numerator with 2 and then the denominator also with 2. So it will be 3 divided by 0.5. That means if in this case, if I travel a horizontal distance equal to 0.5 unit, in that case I will have to travel a distance equal to 3 unit in the vertical direction. Okay, so let us use this concept. So I have reached over here. Now I have to plot the Q line with a positive slope, and I'm going to use this. So I'll have to travel a distance of 0.5, a horizontal distance of 0.5 unit to the right. Why to the right? Because the slope of the line is positive. If had it been negative, you must be traveling it on the left side. Okay? So I travel a distance equal to 0.5, horizontal distance equal to 0.5, and if I do that, the vertical distance that I'll have to travel is 3 unit. So I get this point. So I have this point, I have this point, and now I can simply draw the Q line that passes through these 2 points. So that would be the required Q line. I hope the concept is clear to you. If you have any doubts, you please mention them in the comment section. Okay. Then we need to plot the stripping section line. For plotting stripping section line, we are going to use this information. XW is 0.02. So 0.02 will be located over here. And then I'll go to the diagonal line. Stripping section line will start at this point and it will pass through the intersection of Q line and the rectifying section line. So that will be the stripping section line. So with this, the basic structure that we will be using to plot the stages is ready with us. Okay, so let us plot the stages. So you start over here. We are starting at this point where the XD, the line from XD intersects the diagonal line. Then I move in the horizontal direction. Then I move in a vertical direction to reach the rectifying section line. Then horizontal direction to reach the equilibrium curve. Vertical distance to reach the rectifying section line. Horizontal to reach the equilibrium curve. Vertical to reach the rectifying section line, and in this way the construction will go on. Okay. Now I have arrived at this point. Now when I travel in a horizontal direction, I am crossing the intersection point of the 3 lines. So that means now I have arrived at the feed plate. Earlier I was in the rectifying section. Now I have arrived at the feed plate. Now I have to go to the stripping section. So this time, when I travel a vertical distance, I'll be going to the stripping section line. Then horizontally to the equilibrium curve, vertically to the stripping section line, horizontally to the equilibrium curve, vertically to the stripping section line, horizontally to the equilibrium curve, vertically to the stripping section line, and in this way I will continue doing the construction. Okay. And finally, if you are able to see at this point, I cross XW. The construction of triangles will be continued till XW, point XW is reached. Okay. Now we are left with counting of the stages. So this is stage number 1, stage number 2, stage number 3, stage number 4, stage number 5, stage number 6, stage number 7, stage number 8, stage number 9, stage number 10, this is stage number 11, this is stage number 12, and there is one more small stage that will be the last one, which is nothing but R, the reboiler. Okay. So in this case, you have okay. So in this way, we get the number of stages. So number of stages are 12 plus 1 reboiler, Ni, that is number of ideal stages, 12 plus 1. Stages in the rectifying section, 1, 2, 3, 4 and 5. There are 5 stages in the rectifying section. Feed stage is the 6th plate or 6th stage, and stages in the stripping section, how many are they? 1, 2, 3, 4, 5, 6 and 7. So there are 7 stages in the stripping section. So you have total 7 stages in the stripping section. 1 stage is the feed stage, that is 6th stage, and 5 stages in the rectifying section. So in this way there are 13 stages in this particular tree call. So with this I end my discussion for this particular numerical. So here you have learned many things. You have learned how to convert composition if it is given in wet percentage to mole fractions. Then you have learned how to convert feed flow rate if it is mass flow rate, how to convert it to the molar flow rate. And then you have also learned how to the value of Q for a cooled liquid. So with this I end my discussion for this particular numerical. I hope you have learned something. If you have any doubts, if you have any feedback, you give that in the comment section. Thanks for watching my video. Do subscribe to my YouTube channel. Tell your friends to subscribe to it. And you don't forget to hit the bell icon so that you'll be notified as soon as I'll be uploading any new video. For now, have a nice day and hope to see you soon in my next video.